Have you ever contemplated the immensity of the universe? That infinite carpet of constellations, galaxies, and stars glittering in the night sky? The universe is a vast theater of cosmic wonders, a canvas on which the deepest mysteries of creation are drawn. From the majestic spiral of a distant galaxy to the soft glow of a nearby star, each point of light is a tale of birth, life, and death in this cosmic ballet. In the midst of this great stellar symphony are some discreet but crucial players, the brown dwarfs. Neither dazzling stars nor simple planets, brown dwarfs are celestial objects that flirt with the limits of our astronomical understanding. Too massive to be considered as simple planets, but lacking the power to ignite the nuclear reactions of stars, they represent a fascinating missing link in our understanding of the formation and evolution of celestial bodies. Dear space traveler, welcome. Our expedition is about to begin. You're going to have the privilege of getting up close and personal with some celestial objects whose existence was unknown just a few decades ago. Brown dwarfs. Although massive, these unusual objects have remained in the shadows until recently. Their discovery is of vital importance for understanding the mechanisms of the universe and has necessitated an extension of the spectral classification of stars. But before you set off on this fabulous astral expedition, if you haven't already done so, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! It was in the 1960s that the hypothetical existence of brown dwarfs entered the astrophysicist's sphere. Two Japanese researchers, Chushiro Hayashi and Takanori Nakano, put forward a postulate, as did American astronomer Shiv Kumar of the University of Virginia. In 1963, Kumar suggested that the gravitational contraction that gives rise to stars and large clouds of gas and dust could also create a host of smaller objects. These celestial bodies, with masses too low to sustain stable thermonuclear fusion of their hydrogen nuclei, would be, in other words, aborted stars. In other words, they were aborted stars, not massive enough they wouldn't be able to shine as brightly as their fellow stars. Shiv Kumar called them black dwarfs because of their very low luminosity. According to the logic of main sequence star designations, the names of these dwarf stars vary according to their spectral color, which in turn depends on their mass. Thus, our Sun is cataloged as a yellow dwarf, while less massive stars are classified as orange or even red dwarfs. But the term black dwarf was replaced in 1975 by the American astronomer Jill Tarter, becoming a brown dwarf. Although black dwarfs do exist, they have no connection with the object suggested, as they are the final stage of a white dwarf that has undergone various thermonuclear reactions. However, brown dwarfs have never reached this stage, as their mass is less than 7% of that of the Sun, the minimum required for the core temperature of the star to rise under gravitational pressure. In the 1980s, the theory of potential brown dwarfs proved sufficiently relevant for astronomers to systematically include them in their long list of objects to be detected. However, These dark objects emit only weak radiation, which is mainly detectable in the infrared range. Unfortunately, for researchers in search of a major discovery, the detection equipment of the period was not sensitive enough to bring these mysterious objects to light. It wasn't until January 1994 and the arrival of more powerful equipment that the first brown dwarfs were finally observed, confirming this theory. 3 astronomers from the Canary Islands Institute of Astrophysics, using their telescope at Teide on the island of Tenerife, succeeded in capturing one of these extremely discrete stars for the very first time. This is Teide 1, the first brown dwarf to emerge from the shadows, with a mass estimated at between 40 and 60 times that of Jupiter. Located some 430 light-years from Earth in the constellation Taurus, it was hiding in the open Pleiades cluster. Its cold nature was confirmed the following year, in 1995, by the William Herschel Optical Telescope on the island of La Palma. The following month saw the discovery of Gliese 229b, a brown dwarf orbiting the star Gliese 229a. The observation of this object, about 20 to 50 times the mass of Jupiter, was made possible by the use of a coronagraph, an instrument that artificially dims the brightness of its host star. New discoveries of brown dwarfs soon followed. Many of them were detected close to our solar system, where they turned out to be quite old and faint, as well as at the heart of distant clusters of young stars, where they were still relatively bright. As suggested by American astronomer Shiv Kumar, brown dwarfs have lower masses than the least massive stars, but higher numbers than planets. In short, a brown dwarf is either a small failed star or a gas giant superplanet. Brown dwarfs have masses between 13 and 80 times that of Jupiter. While they are not massive enough to sustain the hydrogen nuclear fusion reaction, they are capable of burning deuterium or heavy hydrogen. This distinguishes brown dwarfs from both planets, which don't radiate their own heat, and stars. Deuterium combustion can last for hundreds of millions of years, before diminishing due to lack of fuel. Even so, this phenomenon doesn't allow brown dwarfs to boast high temperatures. Most of them don't exceed 2,500 degrees Celsius, or 4,532 degrees Fahrenheit, well below the temperature of the vast majority of stars worthy of the name. This explains why they emit very little light in the visible range. Instruments capable of measuring infrared light, a type of luminosity imperceptible to the human eye, are therefore essential for detecting and observing these cosmic objects. What's more, infrared waves are blocked by the Earth's atmosphere, making it difficult for scientists to detect them. Fortunately, new measuring devices are now designed to gather a wealth of data from space. These include space telescopes such as the James Webb Space Telescope, equipped with a Canadian NIRISS device for studying brown dwarfs in infrared light. But let's take a closer look at these atypical stars. Let's start with an obvious fact. Brown dwarfs are not brown, but rather have a dark orange-red or magenta hue. Being less luminous than the red dwarfs already listed in the spectra table, their name derives from their dark color. Brown dwarfs are classified according to their spectral type. Unlike main sequence stars, whose energy is derived from nuclear reactions, the energy of brown dwarfs derives from their gravitational energy, converted into internal energy by contraction. The hottest of these, with temperatures close to 2,500 degrees Celsius or 4,532 degrees Fahrenheit, are M6.5 dwarfs, as are very low mass stars, namely red dwarfs. Next in line are the L dwarfs. Cooler than red dwarfs, their effective temperature ranges from 1,026 to 1,726 degrees Celsius, or 3,138 degrees Fahrenheit at most. They are also distinguished by the presence of dust grains composed of metal oxides in their atmosphere, suggesting episodes of molten iron rain. The next category concerns T dwarfs. Even colder, they have temperatures below 926 degrees Celsius or 1,700 degrees Fahrenheit, and therefore emit little or no visible light. In the spectrum of these stars, we can detect lines of methane or carbon monoxide, whose synthesis is made possible by these low temperatures. Finally, brown dwarfs with surface temperatures of around 230 degrees Celsius or 446 degrees Fahrenheit are Y dwarfs, for which the spectroscopic signature detects ammonia. In the absence of other potential sources of energy in their surroundings, brown dwarfs move from one spectral type to another as they cool. The hottest brown dwarfs, which still benefit from residual heat from their formation, are consequently the youngest, and resemble the smallest stars on the main sequence. It's only after billions of years that they join the Y dwarf category, the coldest of all. The mass of brown dwarfs falls within a fairly wide range. As we've already seen, it can be anywhere from 13 to 80 times that of Jupiter, and must not exceed this boundary equivalent to 0.07 solar masses. Otherwise, hydrogen fusion reactions could be triggered over the long term. Despite this wide range of masses, the diameters of the brown dwarfs vary little. Most of them are slightly larger than the planet Jupiter, by around 10 to 15%. Like planets, brown dwarfs are actually protected from gravitational collapse by Coulombic pressure, the electrostatic repulsive force between protons in an atomic nucleus. Finally, what are brown dwarfs? Are they megaplanets or stars too faint to shine? While it was extremely difficult to distinguish between them when they were first discovered, certain criteria are now measurable. It's fair to say that brown dwarfs are stars in a league of their own and deserve the full attention of the scientific community. But are they anomalies, or are they the missing link that marks the boundary between the heaviest gas giant planets and the lightest stars? Stars are often accompanied by substellar objects such as planets or brown dwarfs. In order to distinguish between these two categories, a number of key factors are studied, enabling us to avoid confusing them. Having defined the mass, shape, composition, and thermal structure of the atmosphere, as well as the orbital trajectory, astrophysicists are now able to classify each observed object. Now let's see what distinguishes a star from a planet. These two objects may appear bright in our night sky, but they are nonetheless different. A star, capable of creating nuclear fusion reactions, shines with its own brilliance. A planet, on the other hand, produces no light at all. It merely reflects the luminosity of a neighboring star. These cosmic objects, with their contrasting compositions, also have different origins. A star is created within a cloud of gas and dust when the latter is dense enough to contract. The star in formation heats up to the point where hydrogen begins to fuse into helium. A star is born as a large dazzling ball of plasma. A planet, on the other hand, forms progressively from gas and dust found in large quantities on the periphery of a young star, notably in its protoplanetary accretion disk. Under the effect of electrostatic forces, these particles agglomerate over time to form a planet of varying mass. When the planet is sufficiently close to the star, it becomes a rocky planet, such as Mercury, Venus, Earth, or Mars. If, on the other hand, it is very far away, it evolves into a gas giant resembling Jupiter. If the boundary between stars and planets seemed obvious, the discovery of brown dwarfs, which are neither planets nor stars, has once again called into question what scientists had taken for granted. Since 1994, numerous brown dwarfs have been discovered, but it was in 2008 that astronomers discovered the missing link between planet and star. A team of French and Canadian researchers who were trying to find brown dwarfs using the MegaCam camera on the Canada-France-Hawaii Observatory Telescope made an extraordinary discovery. Just over 42 light-years away, in the constellation of Cetus, they spotted a brown dwarf with a temperature of just 350 degrees Celsius, or 662 degrees Fahrenheit, the coldest yet detected. Named CFBD S0059, it is colder than ULAS 0034, one of its sister stars detected the previous year, with a temperature of around 400 degrees Celsius or 752 degrees Fahrenheit. These two stars, which surprisingly display ammonia in their atmospheres, were the originators of the new Y-classified brown dwarf category. Ammonia molecules are non-existent in stars whose temperatures is far too high. As a result, these two brown dwarfs can almost be considered planets. This particularly cold star has also marked a turning point for researchers, who can now refine their atmospheric models, particularly for extrasolar planets with similar temperatures. As a result, the boundary between cooler brown dwarfs and planets is getting thinner. But what about the hottest brown dwarfs? How can we distinguish a brown dwarf from a small, frail star that has lost its brilliance? The answer was published in 2013 by Sergio Dieterich and his counterparts at Georgia State University. They cataloged the photometry of 63 brown dwarfs whose spectral type ranged from M6.5 to L4 in a kind of Hertzsprung Russell diagram that classifies low-mass stars. By comparing these data, they found that the radius of main sequence stars decreases as their temperature increases. But below 1,826 degrees Celsius, or 3,320 degrees Fahrenheit, a sudden gap appears in the distribution of low-mass stars and brown dwarfs. The diagram shows that, like stars, brown dwarfs increase in size as temperatures get lower and lower. In this way, the scientists were able to establish precise values for defining the characteristics of the least massive stars on the main sequence. As a reference star, they chose 2-mass J0513-1403, a very low-mass red dwarf, located around 40 light-years from Earth, in the Hare constellation. It is in the final stage of its main sequence, as evidenced by its temperature of around 1,826 degrees Celsius, or 3,320 degrees Fahrenheit, a size 8.7% that of the Sun, and a luminosity equivalent to 1/8,000th that of the Sun. This star at the end of its life thus seems to determine the boundary between stars and brown dwarfs. Nevertheless, no population of stars seems to be willing to fill the gap between these two categories. Could this be explained by a different formation of these stars, or even divergent evolutions? In 2013, the mystery still hangs in the air, prompting astrophysicists to delve even deeper into their observations. In spring 2014, the discovery of a very singular brown subdwarf was announced. Detected thanks to joint observations by the Spitzer Space Telescope and the Gemini Observatory, covering both hemispheres, Y0855 is located in the constellation Hydra, just 7.2 light-years from Earth. Although it is the fourth closest star to our Sun and has 5 Jupiter masses, it remains invisible to the naked eye. While its spectral study has revealed that it resembles Jupiter, it is above all the coldest brown dwarf observed at the time of its discovery, with temperatures colder than ice, ranging from -48 to -13 degrees Celsius, or -54 to 55 degrees Fahrenheit. It is also the coldest object known outside our solar system. As cold as our North Pole, this brown dwarf appears to contain water. According to the spectrum obtained after 14 hours of observations spread over 13 nights, Y0855's atmosphere could take the form of water clouds or water ice, giving it an appearance extraordinarily similar to that of Jupiter. This brown dwarf, with its particularly cool hues, is therefore covered in clouds. On the other hand, its atmosphere contains much less phosphine. A lower content of this gas means that its atmosphere is certainly less turbulent than Jupiter's, which is renowned for its devastating winds. The study of this Y2 classified extrasolar spectrum is of paramount importance to scientists. Having long investigated the dynamic and chemical properties of Jupiter's atmosphere, they can now turn their attention to extrasolar worlds. Y0855 finally gives them the opportunity to study such a planetary mass object, almost as cold as our gas giants. Subsequently, many brown dwarfs were found to exhibit slight fluctuations in brightness. So there are variable brown dwarfs. But what is really the case? In research published in 2017, an international team, based on observations obtained by NASA's Spitzer Space Telescope, suggested a novel model to explain these variations. They are linked to the clouds of iron droplets and silicate dust that partially cover certain red dwarfs. These giant clouds seem to change in less than 24 hours, which is very surprising. Organized in bands at certain latitudes, these clouds are subject to the giant atmospheric waves that swirl around the star. Like waves of varying intensity, these waves carry the cloud bands in their wake, causing variations in the object's brightness. This finding is a real breakthrough for the researchers, enabling them to conclude that the atmospheric dynamics of brown dwarfs are similar to those of the gas giants in our solar system. These cold stars, which have long remained anonymous thanks to this observation, are very likely to represent the famous missing link between planets and stars. What's more, scientists believe that the large atmospheric bands and waves observed on the surface of brown dwarfs are probably also common on giant planets in other star systems. This is why the study of brown dwarfs is fundamental to a better understanding of giant exoplanets, especially as they too are composed mainly of hydrogen and helium. Also in 2017, another major discovery was announced. Lead author Zhenghua Zhang from the Canary Islands Institute of Astrophysics reported particularly exceptional results from an observation of a so-called SDSS J01404 plus 1535. This is a brown dwarf about 750 light-years away in the halo of our galaxy, where there is a population of extremely old stars. He said he didn't really expect to see such pure brown dwarfs, and with good reason. Only 0.01% of the star in question corresponds to any chemical element other than hydrogen or helium. The elements initially present in the universe just after its creation, the famous Big Bang, were none other than these same two components, combined with minute quantities of lithium. This brown dwarf is therefore 250 times purer than our Sun. This peculiarity is probably not as rare as one might think, as the same scientist points out that having found one, however, often suggests a much larger, hitherto unknown population. It would be very surprising if there weren't many more similar objects waiting to be spotted. But this sensational discovery is not limited to the composition of this record-breaking brown dwarf. Its mass is just as exceptional for a star in this category. This failed star, probably 10 billion years old, is 90 times more massive than Jupiter. It is therefore the heaviest brown dwarf ever studied, with a mass approaching 9% of solar mass. Among the abundant data collected by the various satellites in action, some of an exceptional nature remain buried in archives for many years before being revealed. When the European Space Agency celebrated the 20th anniversary of the XMM Newton space satellite at the end of 2019, a discovery was made. This heavyweight of X-ray observations, equipped with the most powerful mirrors ever conceived, had captured images of a gigantic X-ray eruption from a tiny star. This exceptional event, suffered by an L-type brown dwarf named J0331-27, on July 5, 2008, lasted just a few minutes, but it was so intense that it caught the attention of scientists. This tiny star, barely 8% of the Sun's mass and barely able to generate its own energy, was nevertheless the source of a flare, 10 times more intense than the most fearsome solar flare on record. For astrophysicists, this is an incomprehensible feat. For an eruption to occur in a star's unstable magnetic field, it must collapse and release stored energy. Consequently, this eruption can only take place if it is supplied with energy, in particular by ionized particles. Ionized particles can only be generated at very high temperatures, which is paradoxically impossible for a brown dwarf of this type, whose surface temperature does not exceed 1,826 degrees Celsius or 3,320 degrees Fahrenheit. As a reminder, our Sun reaches up to 5,726 degrees Celsius, or 10,340 degrees Fahrenheit, at its surface. Scientists also noted that during the 40 days of observation, no other eruptions occurred on this brown dwarf. This finding is all the more surprising given that such an event is not usually isolated and is part of a series of numerous smaller eruptions. This discovery once again calls into question the conclusions of astrophysicists, who did not believe that a brown dwarf of this type could store so much energy in its magnetic field. According to Andrea De Luca, leader of the team studying the data, it is possible that this type of star takes longer to accumulate sufficient energy before expelling it in a single violent blast. For the time being, the mystery remains unsolved, and future observations of this type should help to shed light on this spectacular anomaly. Another challenge for scientists is to study the winds blowing around brown dwarfs. Measuring the speed of gusts relative to a hard surface like a planet's is easy enough. In the case of brown dwarfs, however, as well as gas giants, which are composed mainly of gas, the task is far more difficult. However, while the upper layers of gas move independently of each other in distinct agglomerations, at depth it's a different story. Here, the pressure is so great that the gas buried at the heart of the star rotates as a single block. The rotation of this inner part is therefore used as a reference for calculating surface winds. In 2020, a team succeeded for the first time in measuring wind speeds on a brown dwarf, named 2-mass J1047 plus 21. Located 34 light-years away, its mass is estimated at between 16 and 68 Jovian masses, with a surface temperature of 600 degrees Celsius or 1,112 degrees Fahrenheit, making it ideal for infrared observation. Thanks to data from NASA's Spitzer Space Telescope, the study of this brown dwarf's luminosity variations has helped determine its surface rotation period, estimated at just over 1.741 hours. To assess the speed of the star's inner lump, scientists turn their attention to its magnetic field. The study of radio waves emitted by this celestial body using radio telescopes has established that the rotation period of the brown dwarf is between 1.751 and 1.765 hours. The difference between the two rotation periods enabled us to determine that the surface winds sweeping eastward over this brown dwarf are blowing at the prodigious speed of 1,116 kilometers per hour. This innovative technique should make it possible to study the atmospheric dynamics of distant worlds, i.e., planets far from our solar system. Some failed stars, too cold to be discovered due to their weak infrared emissions, can now be detected by another method. In 2020, a team of researchers published a study revealing that they had, for the first time ever, succeeded in locating a substellar object by detecting its radio emission. BDR J1750 plus 3809, a cold brown dwarf nicknamed Elagast, was detected by radio astronomers using the LOFAR radio telescope. This device is so powerful that it can pick up magnetic fields comparable to those of a magnet's small electromagnet. So, after the scientists had detected radio images propagating in the form of circular polarization, they continued their infrared observations with the Gemini telescope and NASA's Infrared Telescope facility, confirming that they had indeed succeeded in detecting a brown dwarf. This discovery paved the way for astronomers to detect low-emission objects, such as exoplanets, with features in common with Jupiter. By studying the magnetism of brown dwarfs, which is similar to that of planets in our own solar system, scientists hope to learn more about the magnetism of extrasolar bodies and its impact on exoplanets that might be able to harbor some form of life. Brown dwarfs, only recently discovered, are on the radar of many astronomers. As a result, one revelation follows another in a very short space of time, thanks in no small part to the use of innovative, increasingly powerful technologies. In 2021, it was READ 1b that made the news. This brown dwarf, 17 light-years distant, has an estimated mass of 41 Jupiter masses and appears to be 1.1 billion years old. As you know, these substellar objects are made mostly of hydrogen and helium. However, they do contain a few heavier elements in small quantities, notably lithium. However, during their first few hundred million years of evolution, the internal temperature of brown dwarfs reaches 2 million degrees Celsius, destroying lithium by thermonuclear fusion. As a result, this element is considered a rare material, both in our solar system and in our cosmic neighborhood. To their great surprise, scientists searching for lithium-bearing stars discovered a veritable treasure trove. Concentrating their observations on two binary systems of brown dwarfs, one of them caught their full attention. While the other three are devoid of any trace of this element, READ 1b possesses an unimaginable quantity. According to their estimates, it contains 13,000 times more lithium than our planet Earth. This brown dwarf, which is the faintest and coldest of the four objects studied, confirms that this type of star can be considered the largest deposit of lithium. Battery manufacturers would be delighted to get their hands on such a vein, this rare element having been almost entirely destroyed by our Sun when it was still located in the Earth's core. Recently, in June 2023, a team of astronomers claimed to have identified a brown dwarf that does not meet the usual criteria for this type of object located at the boundary between the worlds of planets and stars. For a start, it has a mass never before equaled for such an object. This brown dwarf holds the record in its class, with a mass of between 75 and 88 Jovian masses. Because of this particularity, the star is at the stellar-substellar limit, just below the lower limit for hydrogen combustion. And yet, while the surface temperature of a brown dwarf is not supposed to reach 2,000 degrees Celsius, or 3,632 degrees Fahrenheit, the one observed here is extremely hot, even hotter than our Sun, which can heat up to 5,500 degrees Celsius or 10,000 degrees Fahrenheit on its surface. WD0032-317b, a brown dwarf some 1,400 light-years away, burns at exactly 7,730 degrees Celsius or 14,000 degrees Fahrenheit. How can a brown dwarf have such a high surface temperature? In theory, this temperature should not be possible, so scientists set out to find why. By observing this brown dwarf, they realized that it orbits an ultra-hot white dwarf at such a short distance that it completes one revolution in less than 2 hours 30 minutes. This proximity, like the Moon's proximity to the Earth, prevents the brown dwarf from rotating on itself, so it continually displays the same face to its hyper-hot neighbor. On the other hand, if its exposed side reaches unpredictable temperatures, its dark side must have degrees between 1,000 and 2,700 degrees Celsius, or between 1,832 degrees Fahrenheit and 4,900 degrees Fahrenheit. This particularity, if confirmed, would make this brown dwarf the substellar object with the largest temperature differential ever observed. However, this exposure leads to a process of thermal dissociation, causing evaporation of the brown dwarf's atmosphere, which will one day fade away entirely. Among the most extraordinary discoveries concerning brown dwarfs, the one nicknamed the accident is probably the most interesting of all. Discovered in 2018 by Dan Castleton, an amateur scientist researching the many images of the WISE space telescope, this brown dwarf, designated WISE J153429.75, has some strange features which explain why it wasn't spotted earlier. Its infrared spectrum, the characteristic that identifies brown dwarfs, is unlike that of other similar stars. The spectrum of this brown dwarf, which we'll call the accident for convenience, is dark where it should be bright, and vice versa. As a result, this brown dwarf is unlike any of its 3,000 or so compasses already explored in our Milky Way. In an attempt to understand these properties, which contradict known concepts, scientists tried to observe it in additional infrared wavelengths using a ground-based telescope. Unfortunately, the object remained in shadow, confirming that its temperature must be extremely low. After thinking that the object was too distant to reveal itself to this type of instrument, they gauged its distance with measurements taken by the Spitzer and Hubble space telescopes. Not only did they find that the object was only about 50 light-years away, but more importantly, its speed was estimated to be particularly fast. This brown dwarf is moving at an estimated 800,000 kilometers per hour, or 500,000 miles per hour. Once again, this brown dwarf doesn't behave like its counterparts, which travel more slowly around our galaxy. What's more, this unusual object contains low levels of methane compared with other brown dwarfs. In the face of so many discrepancies, scientists suggest that these unusual features may not be so strange after all, suggesting that we are almost certainly dealing with a star that is much older than any other in its class. Initially disconcerted, the scientists consider that the particularities of this star make it possible to estimate its age at between 10 and 13 billion years. This would make it twice as old as any other brown dwarf in the galaxy, whose average age is much lower. This brown dwarf has been spinning longer than others, and over time has encountered numerous massive objects, whose gravity has gradually increased its speed. Its low methane concentration also justifies its advanced age. Since its formation probably dates back to the early days of the Milky Way, when it was still low in carbon, massive supernovae would not yet have distributed large quantities of carbon atoms throughout the cosmos. Indeed, a low carbon content at the time of its formation explains its current low methane content. Be that as it may, this discovery is of the utmost importance. Either it's a rare chance to observe an unusual object, or it's a promising one. For scientists, it could well be the answer to the desert of brown dwarfs seen in the Hertzsprung-Russell diagram that classifies stars. Remember that the missing link between an extremely low-mass red dwarf and the most massive of brown dwarfs? What's certain is that astronomers can now recognize old brown dwarfs. It remains to be seen whether they are actually more common than scientists thought. You may not have noticed, but we alluded earlier to a binary system containing a brown dwarf. Just as stars can evolve in multiple systems, brown dwarfs are sometimes accompanied on their long cosmic journey. In 2020, astronomers revealed that they had made a rare discovery while on the hunt for exoplanets. Their quest, carried out with state-of-the-art robotic telescopes called Speculoos, was to detect potential habitable planets in the vicinity of brown dwarfs. Pointing one of their 1-meter diameter telescopes in the direction of an already cataloged brown dwarf, they were intrigued by a strange phenomenon. The object, located 119 light-years away in the constellation Libra, was already faint, but darkened considerably over a period of around 90 minutes. The object, commonly known as 2M1510A, had just been occulted during an eclipse. Observations also confirmed that a second signal was coming from this area, enabling astronomers to envisage a second brown dwarf orbiting 2M1510A. The scientists then realized that they were in the presence of a system much rarer than planetary systems, this one being composed of 2 eclipsing brown dwarfs, one passing in front of the second. The 8-meter telescope in Chile and the large Keck telescope in Hawaii quickly confirmed this suggestion. The 2 elements have roughly the same mass. The first, 2M1510AA, has a mass of 40 Jovian masses, while the second, 2M1510AB, has 39.3 Jovian masses. Assiduous observations have enabled astronomers to assert that the 2 brown dwarfs orbit each other in 21 days. But another discovery followed. These 2 closely spaced objects have an additional companion. Named 2M1510b, it is of the same nature as the binary system already studied. This tertiary brown dwarf, although far removed from the main duo, is indeed part of this system, nestled in a 45-million-year-old cluster of stars known as the Argus Mobile Group. This discovery is of particular interest to scientists. For one thing, the age of the system is similar to that of exoplanets currently under observation. Studying the evolution of these objects, compared to the mathematical evolutionary models assumed, could be of great use in the study of young planets in progress. What's more, apart from 2M0535, no other double-line binary eclipsing brown dwarfs were known at the time. However, the latter remains difficult to observe due to its young age, being part of the Orion nebular cluster, only 1 million years old. Since then, 6 other triple systems of brown dwarfs have been discovered, but 2M1510 remains the only triple system for which the major characteristics of all 3 components have been determined: mass, radius, and age. What's more, these 3 brown dwarfs have approximately the same mass, while displaying the narrowest separation ratios between their different orbits of all, making this triple system even rarer. Following this discovery, scientists were able to cross-check 30-year-old theoretical models of brown dwarf cooling. They found that these models superimposed admirably on the observations, confirming the astrophysicists' hypotheses. The discovery of this system therefore represents a tremendous opportunity to understand how brown dwarfs evolve and cool as they age, and at the same time to better characterize the formation process of young exoplanets. In a closer environment, 6.5 light-years from our solar system, a binary system also made news in 2021. Luminous 16AB, made up of 2 brown dwarfs, is the closest star system to our Sun after Alpha Centauri and Barnard's star. These 2 brown dwarfs are roughly the same size as Jupiter, but around 30 times more massive. Although already known, their close-up observation with the Hubble Space Telescope proved surprising. Not only did it allow us to follow the cosmic waltz of the 2 objects circling each other, but it also helped us collect a wealth of precise data for modeling the structure of the clouds in their atmosphere. After observing the system for 100 rotations using NASA's TESS telescope, the international team came to a surprising conclusion. Brown dwarfs, like Jupiter, don't have spots in their atmosphere, but stripes. Luminous 16b, the more massive of the 2, shows in this polarimetric study thin bands of clouds that allow its light to filter through, as well as other, much darker, and consequently thicker bands of clouds. The latter rotate rapidly around the equator, creating 2 vortexes at the poles. The appearance of this brown dwarf is explained by the presence of powerful winds sweeping across its entire surface. These are by no means localized storms, as the bands run parallel to the equator. Luminous 16b is thus animated by high-speed winds, which, like terrestrial jet streams, mix the atmosphere and redistribute the heat emanating from the star's interior, giving it a striking resemblance to Jupiter. The study of this brown dwarf is of the utmost importance to scientists. It enables them to better understand the climates and temperature extremes of brown dwarfs, as well as their evolution in general, and more generally, the atmospheres of extrasolar celestial bodies. From there, a question is probably burning on your lips. Could Jupiter be a brown dwarf after all? We've just seen that the nearest failed star to our solar system bears an uncanny resemblance to it. The question therefore seems legitimate, especially as Jupiter is the largest planet in our solar system, and the minimum mass required for brown dwarfs is currently only hypothetical and observational. In reality, Jupiter cannot be a brown dwarf. On the one hand, it has insufficient mass to ignite deuterium fusion, which is around 0.001 solar masses, whereas a brown dwarf must have at least 0.012 solar masses to generate nuclear fusion. On the other hand, Jupiter, which has a solid core enriched in heavy elements, formed from the accretion of gas and dust in a protoplanetary disk around our star. However, brown dwarfs composed mainly of hydrogen and helium are born like a star, after the gravitational contraction of an interstellar cloud. What's more, Jupiter has been cooling gradually since its formation, whereas a brown dwarf maintains its high internal temperature due to deuterium fusion over a very long period. So no, although its appearance might suggest otherwise, Jupiter is not a brown dwarf. However, a very recent study published on December 13, 2023, may well have detected the smallest brown dwarf ever imaged directly. Thanks to the NIRCam instrument on the James Webb Space Telescope, a candidate brown dwarf whose mass appears to be only 3 to 4 times that of Jupiter has been spotted 1,000 light-years from Earth in the constellation Perseus at the heart of the IC 348 nebula. This cluster of gas and stellar dust is only 5 million years old, which explains why 3 candidate brown dwarfs have been spotted there, still bright enough to be seen in the infrared. This study has thus revealed this potential floating brown dwarf to be strangely low mass, compared with all those observed to date. But in addition to this unprecedented record, another peculiarity was noted. Low-resolution spectroscopy of these 3 failed stars, which don't exceed 8 Jovian masses, revealed the presence of an unidentified hydrocarbon in their atmosphere. As European Space Agency scientist Catarina Alves de Oliveira points out, this is the first time we have detected this molecule in the atmosphere of an object outside our solar system. Composed of carbon and hydrogen, this molecule has so far only been detected on Saturn and its largest moon, Titan, as well as in interstellar space. For the researchers, this observation is more than surprising, especially as no atmospheric model for brown dwarfs has ever predicted the existence of such a molecule. There is no doubt that the increasingly sophisticated technical means available for observing objects that are younger and less massive than ever before will continue to give scientists the opportunity to make unexpected discoveries. If this object, estimated at between 3 and 4 Jovian masses, is confirmed as a brown dwarf, it will be the least massive ever imaged. It would help advance science, which is trying to answer a fundamental question. What are the smallest stars? Are there even lower mass stars? Stars with the mass of Jupiter? What's more, this discovery poses a new challenge: how to explain the formation of such a small brown dwarf. If the boundary between less massive brown dwarfs and gas giant planets is not yet clearly established, the same is true for the boundary that separates these failed stars from stars. However, the discoveries we are now making at an ever-increasing pace are considerably narrowing these boundaries. Earlier, we touched on a category of brown dwarfs with exceptional qualities, including the most massive ever discovered to date, namely WD0032. In July 2023, a team of astronomers led by Kareem El Bedri of the California Institute of Technology reported having detected a new object of extreme mass, around 80 times that of Jupiter. This observation was made possible by the Zwicky Transient Facility, which is designed to survey transient astronomical objects. This system provides a wide-field astronomical survey of the sky using a new camera installed on the Samuel Ocean Telescope at the Palomar Observatory in California. It can record a wealth of data, including that relating to transient objects. In other words, those whose light changes rapidly. While scientists were on the lookout for low-mass binary eclipses, they detected a system composed of an M-type dwarf star and a brown dwarf. This system has been named ZTF J2020+5033. It comprises an M-dwarf star, the most common of all stars, small and cold, whose exact spectral type is M6. Its radius is 0.176 solar radii, and its mass is 0.134 solar masses, or 140 Jovian masses. Its effective temperature has been estimated at 2,300 degrees Celsius, or 4,172 degrees Fahrenheit. This tiny star's companion is a brown dwarf, whose mass is approximately 80.1 times that of Jupiter, the largest planet in our solar system. It is therefore a substellar object, i.e., a substar unable to fuse the hydrogen in its core, as its temperature of around 1,400 degrees Celsius, or 2,552 degrees Fahrenheit, is insufficient. According to scientists, this system, located approximately 445 light-years from Earth, has another feature that makes it even more incredible. The two objects in this system are closely linked, with the brown dwarf orbiting its star in less than 2 hours. The failed star completes its revolution in just 1.9 hours, or 114 minutes. These two objects present the narrowest orbit ever observed between two uncollapsed stars. For the researchers, this discovery finally confirms that magnetic braking, the process that shortens the orbit of an uncollapsed star around another object, applies equally when the object in question is a brown dwarf. Of the 39 other similar systems listed to date, this one is closer than 34 of them. For the scientists, this singularity, which ultimately turns out to be observed in several cases, prompts them to suggest that brown dwarfs with short-period orbits are not as exceptional as they previously thought. Once again, this is an important discovery, providing a better understanding of the evolution of brown dwarfs and their diversity. According to their projections, the two objects then observed, when they formed several billion years ago, must have been 5 to 10 times larger than they are today. As a result, they were also much further apart. However, this rapprochement is not over yet, and the brown dwarf's mad rush is set to reach a violent conclusion in a few tens of millions of years' time. Although slightly higher, the star's surface gravity will begin to absorb material from its fellow traveler. Inexorably, the brown dwarf is bound to disappear. Will it be swallowed up by its host in a slow but irreversible fusion? Or will a massive explosion occur? In either case, the brown dwarf will disappear forever, while a new star is born. Unless something else happens. In a study published in 2006, scientists report, after studying a binary system using the European Southern Observatory's Very Large Telescope, known as WD-0137-349, that a brown dwarf may well have outlived its mutant star. Located some 330 light-years from Earth, this system is made up of a white dwarf and a brown dwarf, with a tight orbit of just 2 hours. The latter, christened WD-0137-349b, as extraordinary as it may seem, would not have been swallowed up by its hungry companion star in its red giant phase. Prior to this observation, only stars with a mass of around 1/3 that of the Sun were known to persist in such circumstances. And yet, while the main star temporarily expanded its gaseous envelope, as all red giants do, it failed to completely vaporize the brown dwarf. In the process, the red giant slowed its companion's orbital speed, drawing it ever closer to its center in a downward spiral. But the brown dwarf, with a mass in excess of 20 Jovian masses, was massive enough to avoid the worst, even if it didn't qualify as a bright star. Scientists also suggested that the failed star probably accelerated the red giant phase of its host, the engulfed brown dwarf would have accumulated matter, which it would then have expelled back into the cosmos, considerably collapsing the red giant's gaseous envelope. While the phase of isolated red giants is supposed to last around 100 million years, in this case, this one could well have passed through this stage in just a few decades before entering its final stage as a white dwarf. This brown dwarf is therefore the smallest known cosmic object to have survived engulfment by a red giant. Until this unprecedented observation, only red dwarfs had met this challenge. However, the fate of this brown dwarf is far from sealed. Although it has accomplished this feat once, it has only given itself a reprieve and will not be able to thwart its future destruction. Its orbit will continue to shorten, and within 1.4 billion years its proximity to the red giant turned white dwarf will set in motion a process, this time unstoppable. The star will begin to drink in the surface gases of the brown dwarf, which will slowly but surely lose much of its mass. Then, when the white dwarf has accumulated enough material, recurrent novas will occur, until there's not a crumb of the valiant brown dwarf left. Although these dark stars are being observed more and more, there's still a great deal of mystery surrounding them. While we know that they possess some of the characteristics of gas giant planets like Jupiter, as well as features typical of stars, each of their discoveries proves exciting, bringing its own share of surprises. Indeed, in July 2020, NASA made another announcement, declaring that 2 new brown dwarfs with strange characteristics had just been discovered. Their observations, which had been buried in the extensive WISE satellite data collected since 2009, were unveiled thanks to a research program involving amateur scientists. The project, named Backyard Worlds, Planet 9, and funded by NASA, aimed to detect the hypothetical 9E planet, which could nestle at the margins of our solar system, as well as new brown dwarfs. But as the researcher in charge of this project points out, there is still no substitute for the human eye when it comes to recognizing subtle movements in astronomical images. To scan these countless naked eye images, the scientists therefore turned to amateur astronomers. While no planets were spotted, this collaborative study did reveal the presence of 3 brown dwarfs with more than exceptional features. The first, named WO-830, turns out to be the coldest stellar-type object ever detected. The data studied were so unconvincing that Dan Castleton, one of the amateur participants in this study, didn't believe it was real. However, with the help of observations from NASA's Spitzer Space Telescope and its Hubble counterpart, scientists have confirmed this strange discovery. WO-830 does indeed have an extremely low temperature for this type of object, ranging from 26 to 76 degrees Celsius, or 79 to 169 degrees Fahrenheit. For Daniela Bardelez Gaglioffi, lead author of the study and researcher in the museum's astrophysics department, this brown dwarf is the coldest ever detected. But the same scientist revealed another peculiarity. She points out that the coldest brown dwarf previously known belonged to a class of brown dwarfs in its own right, much redder than any other brown dwarf on record, with no explanation for this singularity. This new brown dwarf could well be the famous missing link that closes this gap. For her, there's no doubt that future observations should help to link these elements, and in so doing, understand all the correlations between these faint and exceptional objects. Among the extraordinary discoveries announced during this study, 2 other brown dwarfs stood out. What makes them special? They bear a striking resemblance to the most planetary objects ever found among the Milky Way's oldest population of stars. These 2 atypical brown dwarfs, named WISE 1810 and WISE 0414, have masses equivalent to around 75 Jovian masses and are probably both around 10 billion years old. The former had already been spotted a few years earlier, but was hiding in the plane of the Milky Way, where stars abound. A study of the star's movements over a period of several years confirmed that it is moving fast, and therefore that it is in our solar neighborhood. The WISE images studied have enabled us to classify it as a brown dwarf. The discovery of WISE 0414, on the other hand, is the work of amateur scientists, who, after examining a large number of images obtained by the WISE mission, detected its almost imperceptible movements. While more than 1,600 brown dwarfs and a few white dwarfs were discovered during this research program, these 2 brown dwarfs stood out from the rest, not least for their composition, which proved to be particularly unusual. These brown dwarfs, both around 10 billion years old and each with an estimated mass 75 times that of Jupiter, contain very little iron. One of them contains just 3% more iron than our Sun. Like ancient stars, they have not amalgamated iron from the birth or death of stars in their environment. However, typical similar objects contain up to 30 times more iron or other usual metals. For scientists, this latest discovery is of the utmost importance. It raises the possibility that very ancient exoplanets may have the same property low metal content. Future searches for exoplanets should therefore focus more intensively on metal-poor objects, or those orbiting ancient stars with this same characteristic. For astrophysicist Mark Kuchner, one of the principal investigators of this program, these 2 brown dwarfs, with properties surprisingly similar to those of exoplanets, should enable us to learn a great deal more about the physics of exoplanets. An equally sensational phenomenon has been observed on a brown dwarf located 20 light-years from our Sun. Using radio and optical telescopes, an international team of scientists from the University of Oxford and the University of Sheffield have reported a strange fact, suggesting that brown dwarfs behave more like large planets than small stars. Numerous observations of images, dating back to 2015, have led physicists to conclude that this failed star exhibits powerful aurora borealis, similar to those seen on our Earth. These are reflected in pulses of radio and light that vary periodically as the object rotates. As the object rotates every 2.84 hours, 3 complete rotations were observed in a single night, confirming the presence of a bright element on its surface. Like the Earth and Jupiter, which have strong north and south magnetic poles, this brown dwarf, and certainly many others, is the scene of magnificent aurora borealis, when plasma is trapped in the magnetic field near one of these poles. Electrons then collide with the brown dwarf's atmosphere, which is essentially made up of hydrogen, producing these beautiful luminous effects. Astronomers were extremely surprised by this discovery. while the chaotic magnetic field at the sun's surface causes intense sunspots, demonstrating that stars are adorned with dark spots, while planets display magnificent polar auroras, the object studied calls this postulate into question. In this case, we're talking about a brown dwarf, which belongs to the mass category of stars. However, the scientists had the privilege of observing not spots, but splendid polar aurorae, which are usually phenomena associated with certain planets. Scientists had already accepted that brown dwarfs have cloudy atmospheres like planets, but their clouds are made up of minerals. Now they are able to assert that their magnetic fields, like those of certain planets, are responsible for the aurora borealis. So should brown dwarfs be considered as enhanced planets rather than failed stars? Whatever the case, the weak radio emission of this type of luminous phenomenon has since become a new means of detecting and studying exoplanets. Thanks to the NIRCam infrared camera carried by the James Webb Space Telescope, an international team of scientists declared in spring 2023 that they had identified a binary system with novel characteristics. It consists of two Y-type brown dwarfs, the least massive in their class. While one of the two objects, a close YO-type brown dwarf, had already been detected in 2012, an object observed in September 2022 turns out to be a companion of the same category. We'll call this system WO336 for short. It is located in the Eridan constellation, some 32.7 light-years from Earth. The two brown dwarfs are about 0.97 astronomical units apart, or slightly less than the distance from Earth to the Sun. Scientists estimate the mass of the primary brown dwarf to be between 8.5 and 18 Jovian masses, compared with 4 to 12.5 Jovian masses for the second. Their temperatures are respectively 141 degrees Celsius or 256 degrees Fahrenheit and 52 degrees Celsius or 125 degrees Fahrenheit, the latter being similar to Earth's temperature. These two low-mass brown dwarfs orbit each other with an estimated period of around 7 years. For scientists, the discovery of this pair represents a tremendous opportunity. While they had concluded that most of the massive brown dwarfs forming a system were twins with relatively similar masses, a result explained by the star formation process, they couldn't say the same for lower mass objects such as Y-type brown dwarfs, especially since most closely related binary systems do not have such a low mass ratio. Is this an exclusive system, or does it represent the majority of binary systems composed of ultra-cool dwarfs? For the moment, one thing is certain. With this duo, they have demonstrated their ability to directly measure the masses of the least massive substellar objects, and will probably subsequently be able to determine the minimum lower mass that a Y-type brown dwarf can then present. However, the boundary between the planetary and stellar worlds, while diminishing, still remains a mystery, especially as an upper limit to a planet's mass is still unknown. Although they have long remained invisible, brown dwarfs have proved to be fascinating objects in the course of their discovery. Neither star nor planet, too small to trigger hydrogen fusion and shine brightly, and too massive to belong to the planetary type, they make up a family in their own right. Considered aborted stars, brown dwarfs nonetheless bear a striking resemblance to gas giants. Some have clouds of water in their atmosphere, suggesting the presence of water vapor or ice. Others have been shown to irradiate their surroundings with their powerful magnetic field, protecting potential satellites from cosmic radiation. If their surface temperatures, like their surface gravity, make life as we know it unlikely, could it be that life forms adapted to these extreme conditions exist in a close enough environment? Exoplanets orbit some of them. Could they just be worlds, each more sterile than the last? To find out, we'll need to explore them one day. Brown dwarfs, like silent witnesses to the diversity and complexity of the universe, invite us to imagine unsuspected possibilities, while pushing back the limits of our knowledge.